Calculating experimental probability is not going to be that much different from lesson 40 calculating theoretical probability. As a reminder, theoretical probability, the number of equally likely favorable outcomes divided by the number of equally likely possible outcomes would give us the probability. And if you look here at experimental probability, the formula is not that much different. We say favorable count divided by total attempts count. So the thing that's going to be different between theory and experiment is in experimental probability, you actually do the thing, or someone actually does the thing, and you just count. How many times did I get the outcome I was trying to measure for, divided by how many times did I do the experiment. All right, here's a couple examples.
Exploding kittens. Sometimes you're able to take cards from an opponent. Best card for you possibly to get is this diffuse card. Other cards your opponent is holding right here. What's the probability you pick a random card from your opponent, you end up picking the diffuse card? Choose a card. This guy? Nope. Try again. We'll do this 3 times. You want this one? No? This one? Yeah? Nope. Not the one you want. Last try. Yep, that's the one you're looking for. What's the experimental probability that you get the diffuse card out of your 5, or out of those 5 cards with your 3 tries?
So this one's pretty easy. The probability that Mr. Thomas lands a bottle flip is 0 out of 10. Probability is 0. All right, but do notice in this situation, there's no real way to get a theoretical probability. This is when experimental probability really comes in handy. If you notice, the experimental probability of getting 2 consonants or not getting a vowel seemed very small as we ran trial after trial until the end, and the last 2 trials we got favorable outcomes, and that brought our experimental probability almost up to 1/2 probability. Now I would have to look at the dice to come up with the actual theoretical probability. That would be a good bit of work to do to come up with that. But one thing that you should be aware of is this thing, the law of large numbers. The law of large numbers says the more experiments we complete, the more accurate our experimental probability will be. Okay? That also means that the fewer trials you complete, the less accurate your experimental probability will be. Looking at some math problems we might get with this topic, experimental probability. You got Ray making 15 out of 20 shots, so his experimental probability of making a shot is 15 out of 20, or 75%. All right, you could get that in a calculator by doing 15 divided by 20. That's 0.75. And then either shifting the decimal point 2 places or multiplying by 100. That would give you your percent. Okay, now you can list, same as with theoretical probability, you can list your probability as a fraction or as a percent. You can even list it as a decimal. If he gets a 52 shot opportunities this season, how many goals should he expect to have? So 75%. He's expecting to make 75% of the 52 shots. Okay, so you could do 75% times 52, or you could do 15 over 20 times 52. Either way, we're going to get 39. Right? 39 is the number of goals he should expect this season. 12 out of 20 students in our class failed a test. At that rate, how many students would you expect to have failed each of the other classes? And their sizes are given. All right, so 12 out of 20 is our rate. All right, related to slope in a way. If we were to graph all these on a XY plane, we should end up with a straight line. 60% of the students failed a test. All right, so we would want to be finding 60% of 24, 60% of 12, 60% of 16. You're going to get some decimals. All right, so 14.4 students in that class, 7.2 students in that class, 9.6 students in this class. And I want you to remember that when we're talking about people or objects that can't be split up, you're going to want to do some rounding. All right, so I might say we expect 14 people to fail in the class of 24, and we expect 7 people to fail in a class of 12, and we expect 10 people to fail the test in a class of 16. All right, and again, I'm just multiplying 60% times the number, because from that first class, 60% of people failed. Right? In the last class, not listed, they say 18 people failed the test. How big do you expect that class is? So we're saying 18 out of some number is going to give us 60%. All right, and we want to find that number. And you could guess and check, or you could multiply both sides by question mark, divide both sides by 60%. So 18 divided by 60% gives me my question mark. And then I could just do that in a calculator. 18 divided by 0.60. We expect that there are 30 people in that class. That's using experimental probability to make predictions. So once again, not too much different from lesson 40 in terms of the mathematics that you have to do. It's just where the numbers are coming from, whether it's coming from theory, what should happen based on the number of trials and the number of equally likely outcomes versus information coming from actually doing the trials and counting up favorable outcomes.